Okay, so in this video, I'm going to show you how to calculate sulfur 6 pressure proportions using different available models. So the first thing you're going to do is go to the Read the Docs page, and then you're going to scroll down, and there are two different workbooks here. We are going to work with the top one in this video. So you click on it on the left-hand side, and then you can click here, and it says Download View in NB Viewer. So you're going to click that. And then up here, you're going to see there's a download notebook button. So you're just going to press this, and that's going to go into your downloads. And then the other thing that you're going to need to download for this tutorial is this link here, which is going to go to my GitHub. And again, you're going to press download on that. Then all you're going to have to do is go to your downloads folder on your computer. So here is my downloads folder. You can see these are the two files. Copy those and put them in whatever folder you want to work in. Then you're going to launch Jupyter Lab or Jupyter Notebook or however you want to work with notebooks. And so this is Jupyter Lab, and I've just navigated to the folder where I have put these two files. And you just double click on the notebook and it will launch up and it'll talk you through it. So you're going to have PySolveSat already installed. So if you haven't done that already, I suggest watching some of the more introductory videos because it's going to assume the knowledge from those. So we're going to Shift Enter on Windows to run these various things. So first of all, we're loading PySolveSat. So now what we're going to do is we're going to look at how the different sulfur 6+ models work. So there's three available models in PySolveSat. You've got the Jugo et al. 2010 model, and this calculates the proportion of sulfur 6+ as a function of the deltaQFM value. You've also got the Nash model, which calculates it in terms of temperature and Fe3+ proportion. And then most recently, we've got the method from ONeill and Mavrogenes 2022, which basically calculates the sulfate and the sulfide carrying capacity of the liquid and gets the sulfur 6+ from that way. So these are all discussed in more detail in the PySolveSat manuscript. So to start with, we're just going to look at the importance of correcting for sulfur 6+. So let's say we have a magma with 1000 ppm SCSS. So that means the magma can dissolve 1000 ppm sulfur 2-. Let's say we have an SCAS of 5000. So that means the magma can dissolve 5000 ppm of sulfur 6+. And let's consider varying deltaQFM between -1 and 3. And we're just using a Lin space here. So we're going to get 10,001 equally spaced points between -1 and 3. And then we're just going to look at a few points. So we're interested in QFM -1. So we can basically make a logical statement here. So this is going to read true, false, 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 false. And so basically pulls out the point at which deltaQFM is -1, and then the same for 1 and 2. So the simple function is simply this: calculate S total, SCSS, SCAS. So what you need to do is you need to specify a model. So here we want to use Jugo, and that means that one of our inputs needs to be deltaQFM. So we're going to input this Lin space, and then we're inputting the value for the SCSS and the SCAS. If we run that, you see you get the left-hand column is total sulfur. So this is the total amount of sulfur that the magma can dissolve. It's only showing the first 5 steps, so you're not seeing very, very much. You then have the amount of S2- that you can dissolve, so that's the SCSS. You have the amount of S6+ that you can dissolve, and then the QFM values. And here is probably the thing that's most of interest. This is the S6-S total ratio. So there's various intermediate calculation steps down there. So what we can do to start with is we can try and plot a diagram to visualize what this is showing. So this is a data frame called data frame species. So you can get all the different column headings in this. So I'm just going to run this and then talk you through what the plot is showing. So on the left-hand side, what we've plotted is we've plotted the SCSS as this flat, thin, like magenta line. And then we've got the SCAS as this black line. So at low deltaQFM, you have no sulfur 6+. So the total amount of sulfur, which is the y-axis, that can dissolve in your melt is just equal to the SCSS. Now, as you increase, you have to start applying a correction for the amount of sulfur 6+. And that basically increases the SCSS 2- by a proportion related to the amount of sulfur 6+ you have, because you can have 1000 ppm sulfur 2-, but say 200 ppm sulfur 6+. So your total solubility can be 1200. Now, as you keep going up, you get to this magic point here at about QFM plus 1.3. And at this point, if you keep correcting the SCSS for the amount of sulfur 6 plus using, say, the simple equations from Jugo, you would actually end up eventually predicting more sulfur 6 plus than the SCAS. And you can't have this. You can't exceed the amount of sulfur 6 plus that is the maximum that can dissolve. And similarly, if you were to correct the SCAS for S2 minus, eventually again, when you get to the dashed section of this line, you've actually added more S2 minus back in than is allowed. So what this means is actually the total amount of sulfur that can be dissolved is given by the solid section of the purple line and the black line. And we can show this on the right-hand side. This is the green lines, this is total sulfur. And then in the thin red and black lines, I've shown the amount of S2 minus and sulfur 6 plus that's contributing to that total sulfur. So you can see here that the amount of S2 minus and the amount of sulfur 6 plus never exceeds the SCSS or the SCAS, but it makes this complicated peak shape. And this cyan line is just showing the proportion of sulfur 6 plus over sulfur total in this melt. So you can make these kind of diagrams just using this function. All of these lines are present in that data frame. So for example, total sulfur is the green line. If you want to plot this thin red line, for example, you would just look and you would see that that's S2 underscore total. So this allows you to make pretty plots and kind of understand for different systems where the total solubility of sulfur comes in. So you can mess around with that. But say we care about a natural system. This is much more likely. So what I've got here is a petrolog fractionation model, okay? So I'm going to load this in using the pysulfsat import function. What this does is it takes the petrolog columns and it reformats it into the structure that is required for pysulfsat. Okay, let's calculate the SCSS using the Smythe 2017 model. And in this case, we have to input the liquid compositions, which is stored in this data frame out. We have to input the temperature in Kelvin, which again is found in this data frame, the pressure in kilobars, and the Fe3 plus total ratio. And we also need an estimate of the iron over iron, nickel, copper, sulfur content. So you can input a fixed value, that's what I've done here for kiloweigh. You could also calculate this, and there's other videos showing how to do that. So this tells us the amount of S2 minus that can dissolve in the melt at each point in the fractional crystallization path. If we want to calculate the maximum amount of sulfur 6 plus that can dissolve, I am using the Zoltan-Chazet 2022 model. And you can see that if we calculate that, we can dissolve about 8,800 ppm sulfur 6 plus. So now what I want to do is say, okay, what is the maximum amount of sulfur that can be dissolved? And you can definitely just apply a correction to the SCSS in a lot of systems, but just be aware if you did that without accounting for the SCAS or an estimate of it, you could end up in this dotted section of the pink line, and this is a dangerous place to work. So it's always safer to pick an SCAS model just to make sure you're never ending up with too much sulfur 6 plus, that you're like exceeding mass balance of how much S2 minus and sulfur 6 plus can dissolve. And again, there's more detail of the actual maths behind that in the paper. Okay, so here we are inputting the Fe3 plus Fe total ratio of our petrolog model. We're inputting the SCSS that we calculated up here. So this is the Smythe data frame and the column heading. So here we're using the ideal SCSS. We're inputting the temperature and we're inputting the SCAS that we calculated here. And we're saying that we want to use the Nash model for sulfur 6 plus. And that's why we need Fe3 plus and we need temperature. So we can run this and then we can see that while the SCSS was 1,163 ppm, based on the proportion of sulfur 6 plus that has been estimated, we can actually measure 1181. So you can see here, this is the proportion of sulfur 6 plus over sulfur total, so 0.015, so about 1.5% sulfur 6 plus at the start of this fractionation path. We can do the same using Jugo. So remember, Jugo needs a value for deltaQFM. But in this case, I only have Fe3 plus ratio or a log FO2 value from petrolog. So what we're going to do is we're going to use the Python package thermobar, and you can find this in Volcanica. It was published in 2022. So if you've never used thermobar before, you're going to need to uncomment this line and run pip install thermobar. If you already have it, you're fine to keep that commented, and once you run it once, that'll be it for your computer. And then you just want to check that the version is one of the more up-to-date versions. So now what we're going to do is we're going to use the thermobar function, convert FO2 to buffer. So what we do here is we input the FO2 value from Petrolog. So we have to do 10 to the power of, because Petrolog gives it as a log value. And then we tell it the temperature and the pressure. And then it will calculate delta NNO and delta QFM relative to frost. So we can see here that the delta QFM value is about 0.08, minus 0.08. So what we can do now is we can say we don't want to use Nash anymore, we want to use Jugo. So that means we need to tell it delta QFM, and that is from this data frame, buffer calc, and we're getting this column heading. And then we need temperature, the SCSS, the SCAS, and the model. We can run that, and you can see that this is predicting even less sulfur 6+, so about 0.5% sulfur 6+. The other thing you can do is say you're lucky enough to have Zane's data for your system. You don't need to use the Nash or the Jugo model. You can simply put in the SCSS, the SCAS, and you can put in the sulfur 6+ over sulfur total ratio. So I'm going to run that, and that is now assuming 20% sulfur 6+. Now you can see there's a temperature term in here. We can delete that. And you can see it doesn't change anything. So that's there for consistency of inputs, but it isn't using the temperature. All it's doing is applying the correction math now based on the sulfur 6+ ratio you've given it. Another option if you're working in Daysite is Klein-Sasser released a sort of an empirical expression for the transition based on QFM value. So again, we're saying the SCSS, we're saying the SCAS, and we're saying the model and a delta QFM value we might know for our system. So here we're using a fixed value. To be more consistent, you could also, take this value here that we took. So you can play around with either, depending on whether you trust Petrolog's buffering or whatever you're doing this for. So I can run it like this, or I can input a delta QFM value. And this doesn't calculate the sulfur 6+ proportion. It instead just corrects the total sulfur content. So it's a little bit different in how it works. The final and most recent option is this ONeill and Mavrogenes expression. So the first thing you have to do when you use this is first you want to calculate the sulfur 6+ sulfur total ratio. And this requires you to input your data frame of liquids because the sulfate and the sulfide capacity depend on the major element composition of the melt. So I'm giving it my data frame of liquids, I'm giving it my temperature in Kelvin, and I'm giving it my Fe3 Fe total ratio. So you can see this predicts 1% sulfur 6+ at the start of the model. And now again, I feed this back into the calculate S total, SCSS, SCAS function. And I'm simply putting in this data frame here with the correct column heading, and then I run that. So it's just a two-step process, just so that you can really look at these different variables more simply and check that it's kind of reasonable. So let's plot up the results to have a look. So what we're going to plot first is the magnesium content of the liquid from Petrolog and the sulfur 6+ sulfur total ratio calculated. Initially, this is just our fixed 20% sulfur 6+ for comparison, and then Jugo, Nash, and ONeill and Mavrogenes. And then on the second plot, so this is AX2, so we've got two subplots, we're going to plot the total sulfur that has been predicted. So we can see that these three models really don't predict very much sulfur 6+ up to a maximum of about 5%. So the 20% fixed sulfur 6+ from Zane's, if you got that, maybe that means these models aren't doing very well in your system. And then we can plot the sulfur total versus the magnesium, and you could plot your melt inclusion data on top of this or anything else you had. So that is how you can do various sulfur 6+ corrections.